Good morning from here in London. Thank you for joining us, for giving us an hour or so of your time for today's webinar focused on aerospace. The topic we'll be looking at today will be leveraging design space exploration to improve aircraft ECS system performance. Okay, we're delighted to have two speakers for you today. We have Darrell Rittenberg from Siemens PLM Software, and we have Andreas Bruch, who's our honoured guest speaker from Airbus. I'll just give a couple of quick bios and then we'll get things kicked off. Darrell, as I said, is the Aerospace and Defence Sector Manager. He has over 14 years of expertise related to the aerospace and defence industries. He recently led Tech Pilot Inc. as the Vice President of Product Management and is currently a member of the AIAA Technical Committee on CFD Meshing and Visualization. And again, we're delighted to welcome Andreas, who did a degree program in aviation, specializing in aircraft engineering at FH Jonium, University of Applied Sciences in Graz, Austria. He has been with Airbus from around 2005, and from November 2015 until the present, he has returned to the Air Systems Design Office in Hamburg with a very strong focus on CFD simulation. Okay, so now that we have the bios out of the way, it's over to our first speaker today, Darrell Rittenberg.
Very good. Jay, thank you. And Andreas, thank you again for joining us today. It's my pleasure to have an opportunity to go through some material we feel is quite interesting and topical in the industry. Today, we're going to focus primarily on the role of design space exploration in improving overall ECS system design. This talk will be in two parts. First will be an overview of some of the main trends in the industry, things that are driving innovation, and we will then go through a quick case study related to ice protection systems, which are part of the ECS system. And then we'll go over to Andreas, who will talk about some of the work that Airbus has done using design space exploration for, I believe, a static air mixer case. So with that, let's go ahead and get started, assuming this is going to, okay. So I'd like to at least frame the context of today's conversation in that of innovation. And we use innovation in this context to refer to really the application of technologies. Because what we're seeing in the aerospace industry specifically is that there are a number of technologies that are coming down the pipe that are changing the way people do things. And as Elon Musk said recently, any company that stays stationary with their technology will be exceeded by their competitors. And there's a lot of truth to that statement in that ultimately it's incumbent on all of us in the industry to look for areas of innovation, given the long history of the application of numerical methods in aerospace. This is truly I don't want to say monumental task, but it's certainly a thing that is driving our industry. And a lot of this has to do with how people are leveraging computational methods, and I won't spend too much time on this outside of to say that I would say in the aerospace industry, largely due to work by DLR, ONERA, and NASA for the last several decades, we have quite a few tools and methods that are tried and true that people use for validation of designs as well as troubleshooting design. Well, and typically the troubleshooting in this context is related to things that we run into during test or flight test. Ultimately, though, people are using numerical methods for early design candidates to predict performance. But ultimately, what we're seeing in the industry is a drive towards automation of the mechanics of simulation and ultimately design space exploration. And this has been true of the industry for decades, but as I'll talk about briefly, it's not always easy to move into design space exploration given the complexity of the tools being used. So most organizations have methodologies around validation, troubleshoot, and prediction, whereas highly innovative organizations are really driving up that curve towards design space exploration. And the key is that what are they really looking for in design space exploration? I think this cartoon in a way embodies that, where naturally there are trade-offs for exceptional fuel economy. You have to make trade-offs, and when we talk about design space exploration, what we're really trying to arm analysts and engineers with is the ability to evaluate a design space and understand where trade-offs can be made in the overall system, whether it's between structures, loads, aerodynamics, or propulsion. And this ultimately is what we want to get out of design space exploration. It is not the final design, it's really what drives good design so that we can make better decisions and better trade-offs. So what holds people back? What I've seen in the industry is, at least for the last 15 to 17 years that I've been working in this industry, people have been talking about doing this work, but why hasn't it really taken hold? And a lot of it has to do with four main areas. First is complexity, and in this context, the complexity is in trying to aggregate a system of tools. Putting them all together typically requires a fair amount of IT savvy, as well as, in often case, an understanding of how data transfers between different disciplines. Resources, what we find is that frequently people are hesitant to do these studies because they don't have or don't believe they have enough computational resources to get anything meaningful out of the results. Time, of course, is always a challenge because decisions need to be made on a time scale. So another obstacle people have is not enough calendar time to get these work done. And probably fundamentally, there's a lack of deep understanding of some of the methodologies, and so they become black box. And people, at least to the engineers I've interacted with, this tends to be an area where, given the lack of understanding, there's a lot of skepticism on whether or not the results coming out are ultimately going to be helpful in the design process. So in that context, then, when we think about addressing these challenges, we want to try to move our engineering time from building simple models, testing, in this case, more on the prediction side, and trying to move towards the exploration of a design space and ultimately assessment. So if we can take this engineering time curve and invert it so that we spend more time in the assessment of performance rather than in building of a model, we feel like we can actually help engineers be more innovative in their work. So that's really our goal here today, is to try to move the value curve to where people are spending time. And to do that, we're going to be really having to take advantage of three main areas. One, you need the technologies that can get you there. You need licensing models that aren't cost prohibitive. And finally, you need really someone to help you and assure success by doing a knowledge transfer to help you get up that curve in terms of understanding. Okay. So in that context, STAR-CCM Plus is really set up well. We have parametric models, and I won't spend too much time on this. The five things I think that really help drive this, of course, is flexible meshing. We have multi-physics available, so you can really ask interesting engineering problems. We can scale very efficiently without additional cost, and ultimately automate the workflow. And I think it's supposed to automate, but animate, I guess it's not going to. And then finally, you need design space exploration tools. We'll talk about this briefly. All right, so I want to move now into the main component of the discussion today, which is really about ECS. So thank you for indulging me in 3 minutes here. And let's see if we can leverage what we understand or trends in the industry and how they are impacting design challenges. So one of the things that's very recent is the aerospace industry has signed on, at least conceptually, to the Paris Accords with a notional goal of really being able to be carbon neutral as of 2020, which means that we're looking for in the industry ways to improve overall efficiency. And we know that air traffic is going to be growing at about 5% a year. And the current technologies we have today, we believe we should be able to reduce our CO2 emissions by about 3%. But there's a gap. For us to get to our carbon neutral target, there's a gap in technology. So we're going to need to look for innovative ways to reduce overall energy costs, and that includes looking at the ECS system. The other thing we know is that the number of entries into this market has gone up dramatically. We now have Airbus and Boeing, but there's new entries from everyone from Mitsubishi to Comac to Avid. So a lot of people are trying to get in the industry. So there's more competition, and ultimately, What customers are looking for is an improved cabin experience. So that's a highly competitive market, so we're looking at ways to reduce unwanted noise. We don't want it to be silent, it would be uncomfortable. Increased humidity and pressure, which can help mitigate some of the effects of things like when you travel and you have time differences, and really this jet lag can be reduced if you can improve the cabin experience. So to do this, really we're looking at ways to maximize overall system efficiency within the ECS group, within the ECS systems, improve the overall experience, and ultimately build innovation into the technology we bring to market. And I think for the most part, our industry has been doing that for years. So when we think about ECS, where can you apply design space exploration? There's really a number of areas where it's being used with some frequency. The air delivery system, and that includes the heat exchangers and the mixing. This is an area where people have been using design space exploration. Oftentimes they're using lower fidelity codes for looking at overall ducting problems. From a cabin ventilation perspective, oftentimes the final delivery, so this is the ducting going into the main cabin, obviously cabin ventilation, thermal comfort, in this context looking at the overall comfort of a passenger, the bleed air system, the system that brings air in from the engine typically and provides air into both the cabin or the preconditioner into the cabin, as well as the ice protection system. So there's a number of areas. Other areas you see people using design space exploration include looking at avionics cooling within the cockpit, ice protection systems, and of course, looking at the overall ECS system in the cabin. And what I'd like to do is actually spend a moment talking about design space exploration for ice protection systems. Now, ice protection in this context, we're taking hot bleed air from the engine, and we're actually piping it through a series of piccolo tubes and using that to heat the skin surface of the wing, ultimately to avoid ice accretion. So in this case, we're looking at a relatively complex problem as we are having to look at the impingement of the supercooled droplets onto the leading edge of the wing, and we have to look at the conjugate heat transfer of the hot gases in the ice protection system and look at whether or not we have sufficient heating to avoid ice accretion. And this we've done in the past in terms of just simple melting. So in this case, we actually modeled a thin layer of ice and used the piccolo tube system to ultimately melt that ice. And that was some work we did several years ago. And we showed that, in fact, you could model pretty efficiently this melting phenomena. But that was not really something that we thought would be a good candidate for design space exploration, and we chose rather to look at ice protection under icing conditions and see if we could improve the heat transfer of the piccolo tube system using design space exploration. So in this case, we're looking at a subsection. This is about 10% of wingspan, and we took one of the piccolo tube systems that's used in test oftentimes. This is from AIAA literature. And what we're going to look at here in this context is whether or not we can, just by changing the location of the jets and the relative size and spacing, if we can improve the heat transfer coefficients. So the simulation itself is actually run in two ways. First, we run under ice accretion. In this case, we're looking at the supercooled droplet impingement, collection efficiencies, and we're running this as a start point to understand the thermodynamics on the leading edge. We then model or take that as an input into our model, and we model the hot air from the engine, the impingement on the skin surface, and we look at the overall efficiency over this 10% wingspan. So in this context then, let's take a look at the main parameters. So we first evaluated two main rows. We have top row and bottom row where we can adjust the angle, the pitch spacing between the jets, as well as the hole diameter. So it's a relatively simple system. Our goal was to show that we could do something simple like this in days rather than weeks or months. So the main constraint here is we're looking to make sure that the wing surface temperature remains above 0 Celsius, therefore mitigating the ice accretion. And we want to maximize the total heat transfer on the wing surface. We used a polyhedral mesh in this case. We used a volume control on each jet, so you can see we have higher resolution to better define the physics. We also had, from a prism layer perspective, we actually used on the order of 23 prism layers, so we refined the boundary layer conditions quite well. From an operating condition perspective, we used some values from literature. The inlet gas temperature is nominally 100 Celsius, and the maximum Mach going into the Piccolo tube system was 0.6. We used our steady state solver with a coupled flow, used the coupled flow solver and ideal gas, and using the elliptical blending K-epsilon turbulence model, and of course this was all run RANs. So let's take a look at the results then. So we actually did this in the order of about a day. So in this case, I'm not sure why these didn't. Let's see if we can get these to go. Okay, sorry, they're out of sync a little bit, but basically what we did is we looked at about 35 designs, and we looked at the heat transfer coefficient in watts, and you can see we started off at nominally about 700 watts more or less, and within about 13 generations, we've actually improved that heat transfer to about a little over 1,200 watts, which was 170% improvement in the heat transfer, again, using the same constraints. So what did we learn in this process? Well, we looked at the initial design, which was the simple staggered jet array, which had a heat transfer results of about 700 watts. And within less than a day, we were able to improve by about 177% to about 1,240 watts. And one of the key things, of course, key findings was that by spacing the jets out, and it kind of makes sense in the context of what we know about just the basics of the physics, but by increasing the jet size by about 200% and reducing the number of jets, we actually could increase quite efficiently the heat transfer coefficient. So I use this as an example, as a primer, to give you an idea of the types of systems people are looking at when they talk about design space exploration. And with that, I would like to invite my colleague Andreas to talk about some work that Airbus has done on the bleed air system using design space exploration.
Okay, good day everybody, here from Hamburg. I'm Andreas Roch, and I'm very pleased to give you a small demonstration of what we did together with CDAPCO, respectively Siemens now, for the optimization of a static mixer of our bleed air system. I'd like to start with a couple of words to Airbus itself, what we do, some key numbers of our company, a rough description of the problem that we had. Then I will continue with our first attempt that we did in-house here in 2013. And I will conclude with the presentation of optimization study done with CSIM Plus and Optimate Plus. First of all, some key figures about Airbus. I think many of you know Airbus is quite a vast company. We have roughly 50,000 employees, backlog of 10 years. So for the next 10 years, we have enough orders in our books to produce aircraft. And we have 400 operators that fly with Airbus aircraft. Our family is also quite broad. We have our working course, the A320 family. There are roughly 7,000 aircraft flying today. The topic I'm going to present here today is also taken from the A320 family. We have our long-range aircraft, the A330. There are basically an old version or the classical version that is already in operation since the beginning of the 90s. There will be another version that is where the first aircraft is built now, with the first flight mid of this year. Then our all-new long-haul aircraft, the A350. It's a carbon fiber aircraft. We have also 80 aircraft in operation today, roughly. And our flagship, the A380, which is the hugest aircraft now in operation. When we talk about CFD in environmental control systems, so the domain where I'm working in, we use CFD in many areas of applications. So as you can see, we did a simulation of the flow patterns and the thermal conditions in the cockpit. We did also simulations for avionic compartment. That's here in the lower left-hand corner. But we also do simulation of duct networks, where we try to predict pressure losses, mixing of different airflows, and all other classical stuff. And last but not least, in the upper right corner, you can see a picture of a study of the airflow pattern in the cabin, which is also a quite important task and part of our daily work. Okay, when we look at a problem that that we try to solve using optimization approaches, we have a part here from the bleed air system of the A320. It's located in the pylon, which means it's the part where the aircraft is mounted at the wing. In this area, we have a lot of equipment where the air is preconditioned for later use for all kind of applications in the aircraft. So the study that we did for this premixer here is, as I said, from the A320neo. It's also aircraft where we have, I looked up today, we have 68 aircraft already in operation, and it's going to be an aircraft that will be quite common in the skies. When we look at the problem itself, you can see our bleeder system architecture. Basically, we tap hot air from the engine's compressor, so that is the red arrow in the lower part here. The tapped air can have quite a big range of temperatures. So depending on the operating condition of the engine, in idle you have low pressures and low temperatures. And when we go to takeoff, for example, we have a lot of pressure and also very high temperatures. Of course, we try to cool down this air using fan air. That means air that is coming from the engine's fan. It will be directed through this plenum to this big heat exchanger here, where we try to cool it down to roughly 200 degrees at the outlet of this pre-cooler. This task will typically be fulfilled by a valve that is located here upstream of the pre-cooler, the so-called fan air valve. And the air that we tap from the engine is finally used for two major purposes. First, for the air conditioning system. As you know, we have to pressurize the aircraft in flight, and we have to provide air at a certain temperature and a certain flow to the cabin. And the second major part that we have is the wing ice protection system, something that Durell talked about earlier. And this offtake here includes also a temperature sensor. This is basically the input for the fan air valve and for the temperature control of this system. As I said, major purpose for the bleeder system, air conditioning and wing ice protection system, and we can summarize the design goals, the requirements that we have for this air that we take off, basically in two numbers. First of all, it's the pressure loss between the pre-cooler and the temperature sensor must not be more than 5 kilopascals. Of course, we want to have the pressure loss down because of performance reasons. And in order to have the system working properly, we have to ensure that the temperature sensor sees the correct temperature, meaning we want to have a temperature difference between the highest and the lowest temperature in this duct of below 12 Kelvin. When we first started with design optimization of this geometry, we had a design like this. It was a helical mixer, so basically a groove in this duct, where we intended to mix the air that is quite hot in the upper part of this plenum with the colder part of the air in the lower part of this plenum. And we defined for this static mixer here just 3 parameters. First was the radius of this curvature of this channel. Then the h is the depth of this cut, and last but not least, the width of this cut here. This work was done in the frame of a diploma thesis, which lasted for about 6 months in 2013. And that time we didn't use STAR-CCM Plus in the manner we use it today. Therefore, we had to use a complete chain of tools. First of all, there were several in-house tools that we used, for instance, macro and mobs. I will not go into detail for these tools, as well as commercial tools, such as CATIA version 5, which is used everywhere in our company, and I think it's also used quite much in automotive industry. Then we used the ANSYS workbench for the performance of the simulations and the loop with geometry modifications, and MATLAB for doing analysis of surrogate models that were created based on the CFD simulations before. It turned out that this tool chain was quite challenging because you need to adjust a lot in the infrastructure to get this process running. And we also observed that the 3 parameters turned out to be too much for this process. So in the end of the day, we kept only 2 parameters. First of all, it was the radius. That radius is highlighted in this graph by the size of the dot. So a larger dot means a larger diameter of this coil, and h is the height of this coil. Is displayed here by colors. So red is a larger height of this coil, and blue is smaller. And as you can see, when you do a number of simulations, you get this so-called Pareto front. So you can see that you have a classical optimization problem here. You can either choose between a high temperature gradient here in the lower right-hand corner, where you have a small pressure loss, or you have to go into the other direction where you have a high pressure loss, but a low temperature difference. So these are conflicting targets, and the purpose of the optimization is now to find out the best compromise between these 2 conflicting parameters. As you can see in our optimization, we found that we could achieve a pressure loss of 5,000 pascals, and the point here, this target is illustrated here by this blue line. But we were not able to get down the temperature difference lower than 45 kelvins. So we could conclude that using this process, we were able to improve the temperature difference, but it was not sufficient. The turnaround time was much too long, And finally, we decided to try out other ways, and therefore we went on with a collaboration with CDR Adapco, respectively Siemens, and to look what other means we have. So what we finally came up with was a geometry like this. There were two concentric rows of mixing plates. So we have an inner mixer here, consisting of 3 plates in this first geometry, and the outer ring here also with 3 plates. Then in total 11 parameters. So it's a considerably larger number than we had before. And these 11 parameters are describing basically the geometry. So we can change the number of plates, then the angle of the plates, the curvature, and also the ratio of the diameters here, of the inner diameter and the outer diameters. So when we look at this different designs, we can see that we have a large variety of possible designs. And the approach that Optimate Plus uses is now that the Optimate Plus itself is asking CATIA to change the geometry and come up with all these different geometries, and hand over this new geometry to CCM Plus, which runs the simulations. CCM Plus is then using this input to generate this polyhedral mesh here. Typically, for most of the cases, we ended up with a cell count of roughly 3 million polyhedral cells. The whole simulation was done steady state using a segregated solver, K-omega turbulence model, so SST K-omega. Y plus was in the magnitude of 30 to 100, so a wall function was used. And what is important to mention here at this point is that, of course, when you want to run an optimization, you have to run a lot of cases. So you need to try to get the cell count down, so you get this analysis done in a reasonable time. When we look at the methodology, in every CFD simulation, basically you have to define stopping criteria. So in the case here, a moving average was used to stop a converged solution or something that was judged to be converged. Therefore, a convergence criteria 50 pascals over 1,000 iterations was used, and for Kelvin. So that means that the biggest variation of 4 Kelvin, if a deviation of 4 Kelvin in the frame of 1,000 iterations is fulfilled, if a limit like this is fulfilled, the simulation will stop. If 15,000 simulations were reached, it was judged that the simulation is not converged, and the complete simulation was flagged as erroneous. These plots here, by the way, are giving the baseline design. So we had a starting solution that was used as an initial solution for all further simulations. And as you can see here, you have a converged solution. Then you make a new geometry, a new case, and you get a new result in terms of temperature differences. For all the cases that were run in total, there were roughly 270 cases. A total time of 8 days were needed on 2 clusters, or basically it was 2 times 46 CPUs. So in fact, for the whole study, 2 power sessions were in use for 8 days. When we look at the result of the baseline, you can already see that we have a strong temperature stratification. As I said before, it's cold in the bottom and hot in the upper part. And this stratification is also maintained further downstream. So this plane here represents the plane where the temperature sensor is located, which means that if you have different conditions, perhaps a lower flow, the temperature sensor might not measure a representative temperature, which is a problem for us. And when we look at the maximum difference here, we have roughly 150 kelvins of temperature difference. And if you remember, our target was 12 Kelvin. Yeah, this stratification is also highlighted here in this streamline plots. And more importantly, you see that you have this stratification also here in the branch that is going to the wing anti-ice system, which is clearly not desirable. Once 211 simulations were run, you get a plot like this. So we can see here the same tendency. You have a high pressure loss with a low temperature difference, and high temperature difference with a low pressure loss. So, and one thing when we look at such a plot, what we can conclude immediately is that there is no such thing as a best design. So we will always be faced with a compromise between delta D and delta B. And in order to find out the best compromise, the optimization algorithm has to search the complete design space. So an exploration is done in areas where we have low temperatures as well as high temperatures. And we will also later see that we have two major areas of interest. So first area of interest is here where we have a low delta D, and the other one is low delta B. And as we are mainly interested in a low pressure drop at a reasonable temperature difference, later on a single objective optimization was run, where we just focused on this area here, where we have a certain pressure loss and acceptable temperature difference. So in this first set of simulations, we could reach the target of our 5 kilopascal pressure loss, but we still had a temperature difference of 16 Kelvin. If we take a look at the history of this analysis, we can see how the solution or the optimal point is developing. So all these points represent single simulations, and the blue line here is illustrating the best design at the point that we are looking at. So we can conclude that we reach a minimum temperature difference of 20 Ks, which is quite close to our target already after 100 simulations. So this is quite fast. And when we then take a look at the design that were used to reach this, we can already see the direction in which we are heading. So when we look at these different geometries, we can see that the best designs here along this blue line always have small number of plates, small curvatures, which is understandable because the flow in the core region is already mixed well or close to the mean temperature. But the outer regions of the flow regime in this duct is not well mixed, which means that we need to place our plates exactly in that region. So as I said before, once we reached already quite a nice geometry, we want to optimize that region a little further. Therefore, additional 57 simulations were done, where we only focused on the temperature difference. These additional 57 simulations in the end led to 5 designs that were still better than the best design that we saw before. And there were 3 out of these additional designs that were even better in terms of 25 kelvins. So the best design that we found in the end was quite close to the target of 12 Kelvin for the temperature difference, and still within our limits for the pressure drop. And when we want to take a closer look what the main influences are, we can use a plot like this, where every line represents one case that has been run. And as you can see, all the blue lines here are simulations, or respectively designs, where we had pressure loss between 5 kilopascals, which was our target. The red ones here fulfill our target in terms of temperature difference. And the green ones are the ones who fit both. So we will focus now on the green lines, which are basically the best designs. When we look at the number of outer plates here, we can see that all the best designs have a high number of plates in the outer region. That's what we already concluded before. It's just a different type of presentation. And the inner plates have a low number here. Then looking at the curvature, we see that we have a high angle of attack of the plates in the outer region here, whereas we have to have a small angle of attack of the plates for the inner plates. And further on, we can see that the ratio, the diameter ratio of the inner and the outer part is always in the range of 0.5. That means that the quarter of the area is outside. So again, looking at the results for the best design, we have a high number of plates outside, a low number of plates inside, and when we look here at the comparison between the initial design and the final design, we can see that we have almost a homogeneous temperature here at the area where the temperature sensor is located, meaning we have a maximum temperature difference of only 13 Kelvin, and we're within the limits of our pressure loss. And we can also see that the mixing quality, or the mixing is happening quite fast. So if we conclude now, we saw a significant improvement of the temperature difference, which was essential for us in terms of robustness of our temperature control system. And we satisfied our 5 kilopascal pressure drop constraint as well. We saw a turnaround time of less than 2 weeks for the complete optimization process. And then we saw also some limitations in the geometry. So when we want to improve the whole process, it is perhaps required to have a better CAD model, because when you do a parametric model in CADIA, you have to include, it is quite easy in CADIA to get a constraint that is not working. So then you will not even start with a simulation, because the creation of the model itself has failed. So in this analysis, in this investigation, there were 30%. And there might also be a possibility to change the direction of the plates to get even better results, but that was not investigated in that case. I also need to say that as we did this investigation just last year, where the design for the A320 for the actual flying geometry was already frozen, this design is not flying actually today on the aircraft, but it still highlights that for future investigations we will have definitely a benefit when we use this method in order to find out better designs faster. And that concludes my presentation, and I would be happy if I could answer some questions from the audience.
Okay, so it just remains me to say thank you to our guest presenter, Andreas Ruch from Airbus. Thank you to Darrell Rittenberg, and of course thank you to you all for attending. With that, the session is closed. Goodbye.